Now, I would like to show you how to find potential due to weather line charge or surface charge. Let's see example 8. The question is, find a potential at any point on z-axis from a ring on z equal to 0 plane of a radius a and charge density rho. That is the information given. So you have to sketch. Okay, this is SYZ axis. We have a ring located on z equal to 0, which is on SY axis. The radius is a, and the charge density is rho. Okay, so rho is basically rho L. Right, so as usual, if you want to find the potential or electric field intensity from the charge distribution, you have to take sample. So here, I take a small sample of charge, and then let's say the sample give you the small voltage. Okay, this is basically a conclusion from the Coulomb's law. This is what we derived in chapter 2. So I just put it there. Alright, the general expressions for potential V is equal to Q divided by 4 pi epsilon naught R. So you have to alter these equations. So we change to dV because we take a sample. So we change to dV is equal to dQ, right? The sample of charge, which is equal to rho L dL. Then, if you want to find the potential, okay, due to the total charge in the system, so you have to do the integration as usual. So our integration is towards dphi. So we have our dl here is equal to a dphi. So our integration from 0 to 2 pi rho L a dphi divided by 4 pi epsilon naught R. So this is the solution of our integration. How you get this? Okay, so basically our phi is equal to 2 pi, and then we have R. The R here is this distance, which is equal to surd a square plus z square. So just using the theorem Pythagoras. So we got surd a square plus z square volt. Okay, this is the final answer because we can cancel this 2 pi with a 4 pi, and we got rho L A divided by 2 epsilon naught surd a square plus z square volt. This is the answers. Next example. Okay, this is a potential due to the line charge. Next, how we can find the potential due to the surface charge? Let's see example 9. A uniform surface charge density of 20 microcoulomb per meter square is present on the spherical surface of radius 0.6 meter. The question, find potential at this coordinate. So R is 1, theta is 25 degree, and phi is 50 degree. And then B, you need to find VAB, where given A at 2, 30, 60, and B at 3, 45, 90. Alright, this is the questions. You have first absolute potential, second is potential difference between A and B. This is a spherical coordinate. So the solutions, okay, you have to sketch to help you to answer the questions. So this is our sphere. Okay, the radius is 0.6 meter and this has a charge density of 20 microcoulomb per meter square. Alright, we have two graphs. Okay, bear in mind what happens if we have a hollow sphere. Okay, which is the charge only exists on the surface of the sphere here. So for the E field, right, this is our boundary. Okay, we have a radius of 0.6 meter. So the E field is maximum when R equal to 0.6 meter and then it's going down. Okay, it's going down in the factor of 1 over R square. And then for potential, okay, you can see that below 0.6 meter, so the potential has value, but the value is constant. Okay, why? Because I already explained in our previous subtopic. And then it's going down when R start going further from 0.6 meter by the factor of 1 over R. It's based on the equations. So, okay, let's draw back our chart system. We have this chart system, okay, and then I draw a Gaussian surface at 1 meters. Next, we have 2 meters and we have 3 meters because that is the surface of interest. And we have point A and point B. Okay, for question A, V at 1 meters, okay, is equal to Q divided by 4 pi epsilon naught R. And the Q here is equal to rho S ds because we have surface charge densities. So we put all the value. Okay, the solution for rho S ds equal to rho S 4 pi a square. This is basically the surface area of a sphere. So we already proved at the previous chapter how can we find the surface area of the sphere, okay, using spherical coordinate. So you have to do integration with r square sine theta d theta d phi. Okay, the theta is from 0.2 to 0 to pi and phi between 0 to 2 pi. So you got 4 pi a square. So you just can write here 4 pi a square, where a here is equal to 0.6 meter because our charge system is at 0.6 meter. So the total charge is equal to rho S ds. That's why a equal to 0.6 meter. And what below? We have 4 pi epsilon naught R, where R here is equal to 1 meter because we want to find potential at 1 meter, which is outside our charge system. Next, we insert everything. Okay, we have a rho S equal to 20 microcoulomb per meter square, and our radius is equal to 0.6, and R equal to 1 meters, and your final answer will be 813.17 kilovolt. Okay, that is the absolute potential at 1 meter. Next, for question B, you are required to find the potential difference between the point A and point B. Okay, so which is VAB? VAB equal to VA minus VB, where VA is the absolute potential at point A, and VB is absolute potential at point B. From here, so we go back to this figure, okay, like I mentioned earlier, the E field inside the hollow sphere will be 0, while it become maximum at R equal to A, and then it start going down with a factor of 1 over R square. Compare with potential. Inside the hollow sphere, we have potential value which is constant. V is maximum. It has a constant value. And when the potential going outside the sphere, so it will reduce, okay, by the factor of 1 over R. Please remember that. Alright, so we have VAB equal to VA minus VB. And then you have to remember, okay, VAB is equal to Q divided by 4 pi epsilon naught 1 over RA minus 1 over RB. In this case, your Q is equal to rho S ds equal to rho S 4 pi A square. And when you divide this Q with the 4 pi epsilon naught, alright, so this can be cancelled out. So what remains is rho S A square divided by epsilon. And then you put everything, and your final answers will be 135.53 kilovolt. So this is RA equal to 2 meters and RB equal to 3 meters. From here, we can see that we don't care about the location of point A and point B at which theta and phi, because the critical factor is R. Once the point is anywhere on the same Gaussian surface, it has the same potential. We don't care about the theta and phi. So our V is depend on only radius. Right, so we settle this part.